Alright, so we're going to track the motion of a two-dimensional collision for the air hockey modeling. So we'll open Tracker. And once that's open, we're going to drag in the video of the two-dimensional collision, which looks like this. And I'm just going to make my window as big as possible here. And we can have a quick look at the video. There's our collision. Let's just check that one more time. Okay, and the first thing we want to do here is define our origin. No, in fact, actually what we want to do is we want to set up the time and space for this video. So time, we use this clip settings button. The frame rate is 30 for this video, and we can use a step size of 1, I think. Let's just check how many frames we've got. Yeah, step size of 1 will work just fine. And then the next thing we want to do is set up how large this thing is. Now, each of these pucks has a radius of about 8 centimeters. So I'm going to choose New Calibration Stick, and then I will hold down Shift, and I'm going to choose one end of this white circle here, the outer one, and then the other one. And I'm going to zoom in just so I can get this right. I'll zoom in a bit more. And I want this line to go from one white end to the other white end and pass through the middle of the puck. That way it's the diameter, and that is 8 centimeters. So that's 0.08. Okay, and then we can right click on that and make it invisible. And then we'll zoom back out to fit so we can see the whole video. In fact, I'm going to just get rid of this plot view for now, so I have a larger image of the video. And now what we're going to do is we're going to skip ahead to the frame where we can clearly see the middle of this one. So when the hand is out of the way, which is here, and I'm going to make this frame, which is frame number 4, my starting frame. So I'm going to drag this little black arrow to frame 4. And so now I'm ready to track the motion here. So the first thing I'm going to do is just track the motion of this moving one. You can see that the frames are a little bit blurry because this was shot at quite a low frame rate. I'm always going to choose the front end of the middle for each thing that I track. And there aren't very many frames here, so it's okay to track it manually. Also, it'll be easier to track manually because of this blurring. So I'm going to hold down Shift. So what I did, in fact, I'll just explain what I did. I created a point mass. Whoops. And I'm just going to delete this one because I've now created 2. And then I'm going to click on that mass A, and hold. In fact, I'm going to change the mass of this one as well. So I'm going to define the mass, and the mass of each of these pucks is 50 grams. So I'll double click on expression here next to M and make it 0.05 kilograms. Then I'm going to hold down Shift, and as I said, click on the front end of this. And I'm going to keep clicking on the front end of that blur after the bounce as well. Now that puck is leaving, so I only really want to track up to there, and so I'm going to bring this back to that frame, which was there. So now I've dragged that arrow. So now the only bit of this video that we're going to be working with is the bit that's between these black arrows. So now I'll click back to the start, and I can just have a look at that, and we can see the change in motion of that first puck. now that we have that, in fact, I'm just going to show all steps like this. I want to kind of line up my axes so that the initial motion to the right puck is along the x-axis. So I'll click that, and it's almost right as it is. I'm not going to worry too much about where my origin is, but I want to line up this line with that initial motion, so it's traveling exactly in the negative x direction. Then I'm going to make my axes invisible again. Now the next thing we want to do is to add a momentum vector to this puck. So I'm going to get rid of this x thing, and I'm going to add velocity vectors here. And instead of having all steps, I'm just going to show no trails. And I'm going to skip ahead to a frame where I can actually see the velocity vector. So there's the velocity vector. To make that a momentum vector, I'm just going to click this times m. You can see it's now become p instead of v. That's momentum. It's very small, so I'm going to scale it up a little bit. I'm going to scale it up to times 8. Maybe that was a bit too much. I'll scale it up to times 4. And then I'm going to go to track, mass A, and change the velocity footprint to be a big arrow. So here's my momentum vector beforehand. So I want to copy an image of this before the collision. So then I'll just go track, mass A, no, in fact not track, I'll go to edit, copy image, main view, and that will copy that. If I want to have a little bit more detail, I can zoom in a bit more, like so. And just go to edit, copy image, main view. Okay, and we want to write down the size of this momentum as well. So if I click on that momentum vector, the size of it is given here in p, and for my particular frame that I've chosen, the momentum happens to be 2.862 times 10 to the minus 2. So that's 0.02862. Okay, so that's the momentum beforehand. And now what we want to do is track the motion of the second puck. So I'm going to zoom out to fit, and I'm going to go create point mass. And for this one too, I'm going to define the mass, and it was 50 grams. .05, and we'll close that. And now I'm going to track this one, so I'm going to hold down, I'm going to click mass B. In fact, mass B is selected, I can see that here, so I'm going to hold down shift. I'm going to track this mass. And I'm going to again use the front of the blurry line here. And now it's disappeared, so that's where I'm going to end my track of that one. Okay, and now we can show what that looks like here. I'm just going to bring the X back. Okay, in fact I'll turn off. If we leave it at short trails and just get rid of this, in fact we'll put in all steps so we can see them all. So that one started off not moving and then ended up moving this way. Alright, and now we want to add a momentum vector for the second puck and import an image showing the final momentum of both pucks. So we'll click velocity here, and we'll have times m, which we already have, so they're all momentum vectors now, and I'll get rid of the points, and I'll get rid of the trails. And now I'm going to also make those ones bold. It's a big arrow, and we'll skip ahead until we can see the final momentum of both vectors. So there we go. Those are the final momentums of both vectors. And I can export an image of that by going to Edit, Copy Image, Main View. And we can write down the final momentum of both pucks. So the final momentum of this one, we can click on this momentum vector, and we can see that it is 0.01342. And we can click on this one, and we can see that it's 0.02424. Okay, so now I have the size of all of those. One interesting thing that we can do is just drag those vectors in this frame like so. We can add them to each other. And you can see that these two vectors would add up to a vector that goes like this, which you should be able to compare with the initial momentum. Oops, I got this around the wrong way. Let me just do this. Okay, and then we want an image showing the force acting on each of the two masses during the collision. Now the force is related to the acceleration, so I'm going to untick this. I'm going to turn on acceleration, and then I'm going to go times m. And you can see at the moment there are no forces acting, and that's because they're not colliding at this instant. I'm going to scale these up as well. I'm just going to find out how much I need to scale them up by. So the force should be acting here, and I will scale them up by 16 times. So it's the force that causes the change in the motion of the two. I also really want these force vectors to be bold, so I'm going to change the footprints to those to big arrow. And then the same for mass B. And now we can have a look and see what happens. So we have a big force acting just during the collision. We want to have an image of those during the collision. So there's a good image of the two pucks colliding and the forces that are causing the change in motion of the two pucks. Obtain a force diagram for each of the two pucks. So a force diagram, so this is a graph, so we'll click on this. And if we click on here, we can see that force isn't actually on here. So we're going to define a new quantity called, so we'll add a data function, we'll call this force. And that's going to be m times, and we want acceleration magnitude, so that's just a. So this tells me the size of the force acting on the puck. If I click here now and I choose force, I can see that there's no force acting, and then there's a big force, and then afterwards there's almost no force acting. The slight variations here are just because of my bad tracking. So if we have a look at what happens, there's a large force during the collision and there's no force at any other time. So we can export that. That's for mass B. And we can do the same for mass A. If we change here to mass A, and we choose, in fact we need to define that for this one as well. So we go add, and we'll call this force. And it's m times A, enter. and then we look at a plot of that, we can see that it looks almost exactly the same as it did for mass B. Reaches a maximum peak here of about 0.3, which is just the same as what this one did. So we can see here that during the collision we have a maximum force acting at this moment, and the force is in opposite directions as shown by these two arrows, and the force is the same size. So Newton's third law says that whenever you apply a force to something, that applies an equal and opposite force back to you, which is very neatly shown by this diagram and these two graphs here. We can also work out what the impulse is. The impulse is the area under a force time diagram. And so what we can do is go to View and Data Tool, and we can analyze here. So what I'm going to do is I'm going to choose these points during the collision, and I can go to Analyze, or I can go to Measure Area, and then I can just drag these lines, these lines here, to choose what area I want, and I want to just have the area for the collision itself. And during the collision, the area here, which is the impulse, it's force times time, is about 0.0279. I can copy that under Edit, Copy Image. In fact, I don't need all this mess here. Edit, Copy Image, and that will copy everything here, including the area down there. Okay, and I can do the same for mass B. I'll go View, Analyze, and then I can measure the area, and once again I'm going to just choose the area for the time during the actual collision. So I just hover over these gray lines and I can drag them to select an area, and here this gives me the impulse on the other puck. And so we can show that that impulse, technically the impulse is the change in momentum, and so the change in momentum of one ought to be equal and opposite to the change in momentum of the other, and if they are, then momentum will be conserved. Alright, now the next thing we want to do is just show the motion of the center of mass during this collision. So all we need to do that is go Create a center of mass, and we want to include mass A and mass B, and it will automatically use the masses that I've put in and their positions to figure out exactly where the center of mass is. And if I skip ahead here, in fact that's not visible, it is visible, but this is not turned on, so there we go. The center of mass here is this green dot, so we can observe the motion of the center of mass. It's pretty much constant. It's a bit confusing with all these vectors here, so I'll turn that off. So there we see the motion of the, if I show trails, we can see that the motion of the center of mass is a straight line, and that the dots are evenly spaced here suggests that the velocity is constant, which is also shown by this position graph. In fact, if I go to velocity magnitude here, we can see it looks like it's changing a lot, but that's because it's zoomed right in here. So if I make this graph a bit bigger, if I include 0 in my graph here, like so, and I zoom out a bit, you can see that the velocity magnitude is very close to maybe like 0.28 throughout the motion. It might be easier to see that on this graph, that the velocity, that the position is changing at a constant rate. And so the velocity of the center of mass, we can find that by again doing an analyze here, and then analyze and doing a curve fit, and we can see that our straight line fit is a very good fit here, and the gradient of that is about this is times 10 to the negative 1, so about negative 0.27 or 0.27 meters per second. Okay, the last thing that we can do is look at kinetic energy and see if that's conserved. That would make it an elastic collision. So if you look at the red one here, we can get a kinetic energy graph that looks like this. I want to include 0 here. So the starting kinetic energy is somewhere close to 0.0095 or 9, and the ending kinetic energy is 0.0015-ish. And if we look at mass B, we can see that it starts off with no kinetic energy because it was stationary, and it ends up with about 0.0055. And what you can do is look at the starting and ending kinetic energies of these. I'll obviously copy both of these graphs into your report, but then you can add up the total initial, which is just the red one's kinetic energy, and the total final, which will be the kinetic energy of the blue one and the red one, and see if the final and initial are approximately equal. And if they're not, where would the other energy have gone? So there was an interaction here where the two collided, which would have resulted in both heat and sound being produced, which ought to account for the difference. Alright, so that's basically all you need to do with the analysis of the 2D collision.